let's do a revisit the Hadamard gates on Q0, Q1. It's not the interference, that's a superposition, also not entangled. So that will be Q0, Q1, just apply the Hadamard gate. And this is basically yeah, this basically become the for the operation we can do the convert this into with the identity for easy formulation we can change that to this. So and then first step one will be Hadamard gate tensor product with identity gate on the cat 00. And this basically is a superposition of the cat 00. The first bit, we flip the first bit, first Q0. By the way, IBM Q sphere use the opposite order in according to the conventional like quantum physics. This is actually common, like when computer plot things, we often plot from top down, but mathematically many of the plotted from bottom up. I didn't realize in previous lecture that the order are exactly opposite. So basically, when we write in linear algebra, the bits are just opposite to the what is displaying, visualized on the IBM composer. So in this case, the first bit is Q0. The second bit is Q1. So, but IBM put the order just opposite. Yeah. So okay, that's just but it really doesn't change all the meaning. So it's just a way of visualization. And then we step. Oops, that's a red. Step 2, we do the identity with the Hadamard gate on the previous result. On that result. Here, which basically become the and this actually when we expand this one out using linear algebra, it basically become the basically all the states had an equal amplitude. So this is basically become all the state had equal amplitude. What this also means, the final state is actually using linear algebra, the final state is basically also this. So that will be 0, 0, 0, 1, 1, 0, 1, 1. On the IBM Q sphere, this probably actually come to IBM Q sphere, see how it is displayed. So, can I have a 0, 0 is here, 1, 1 at the south. That's north, that's the south. That should be north, south. 0, 1 must be the second one. So you can so on the left we can see the 0, 0, 0, 1, 1, 0, 1, 1. If we go back to the quantum composer, like for example, if I remove the second Hadamard gate, the Q1 should always be 0. You see which one is always 0? The first bit. So now in IBM quantum computer, the first bit is 0, 0. So Q1 is 0. But if I move the Hadamard gate to the bottom, to the Q1, you will see which one is now 0 and 1. It's first bit. So the first bit, the leftmost bit is Q1. But in the most quantum physics or quantum computing, mathematically, the leftmost bit is actually Q1. So that's, I mean, as long as we know that's the difference, it's okay. But sometimes I think last time, the first 2 lecture, I didn't realize the bit flipped. Sometimes I thought I made a mistake in one of the previous lecture. I thought I made a mistake, but don't know how to correct it. But it turned out it's because IBM visualize the data in the opposite way. I didn't realize that when in the previous lectures. So,
are you talking about the little endian and big endian, you mean, Doctor?
Exactly. Yeah. Exactly. Yeah. Exactly. Okay. So yeah. So apparently, IBM.
But I use the little endian, right?
To be honest, I forgot the definition of little endian because I just know they're opposite. So. Yeah, and one is left to right, the other one is right to left. Which one is the bigger?
The smallest one would be the first, right? That's a little endian. That's called endianness. The order of bytes, basically.
Okay, thank you. I forgot the definition. You are right. One is the bigger ending, one is the little ending, but I forgot the definition of a bigger and a little ending. Can you explain that again? Can you type into chat window? Thanks for
big endian is where the most significant bit is on the left.
Yes.
Oh, that's the definition of big endian.
Yeah.
Oh, that means the quantum physics use the big ending.
It's actually, there are some computers use the big endian, some of them use the little endian. So it depends on the manufacturer, basically.
I see. Yeah. Okay, thanks. So is IBM use the bigger ending or little ending here?
It's using the little endian, I guess.
You think it's a little ending? Okay.
Yeah, I think they mentioned that in the beginning.
Oh, is it?
Yeah.
I see. Okay, sorry, I missed that. Okay, thank you. Yeah, I apparently that part wasn't caught my attention. So I may in probably one of the lecture I thought I made a mistake trying to correct it, but I couldn't figure out why I made the mistake. But apparently I know later on realized it's because the IBM, the way quantum physics write is just opposite. So okay, it's good. Now we clarify this now. So in a way, this is actually a definition why this is not entangled, because those are just linear combinations. So, and those are not linear. It's a tensor product. Basically, that will become the tensor product. This basically. And this basically is the can be rewrite as a tensor product of which is what? That one. Oh wait, no, that is not 1 Is that 1 Yes, it is 1 Sorry, yeah. So now it's a tensor product of the two base. Yes, yeah. So this and then by definition not entangled. Yeah. So 2 edge gate on Q0 Q1 is basically become the 2 superposition tensor product of 2 superposition leads to the 2 qubit state system. So, okay.
I have a question, Professor.
Yes. Yeah.
Okay. In the previous one, we did the normal product where they were in the same line. I mean sequential. But now we have H and I. Both of them are sequential, right? The Hadamard and the identity. And then we did the tensor product in this case. Why we did here tensor product and there we didn't do that? It makes sense if it is like parallel, like H and H, directly we make the tensor product instead of.
Oh, I see. Because the H is not applied to the same qubit. When we apply the H here, these 2 H they are applied to a different qubit, different position in the matrix.
Yeah. So why didn't we make from the beginning like the tensor product together? Why didn't we enter the identity then?
Oh, you mean I guess that's easier to calculate. Otherwise, it will be a H. I guess will be H with H. That's actually.
So is it the same when we have like H and H together tensor product? That's my question.
Yeah, let me. That should be the same, I think, tensor product. I thought we did a calculation of that before. Let me see whether we have it or not. Or maybe not. No, we didn't. I actually had that in my note. I guess I didn't mention that in class. Yeah, and then we just directly apply that tensor product is a bit confusing. Yeah.
Here in this example, that's what we did last class, right? This one, the one in front of us.
Right.
They are actually parallel. So we made the tensor product here. And there we have H and I in the sequential. So
no.
Why did we make tensor product again?
This is not sequential.
This is parallel, right?
Yeah, it's a parallel. Yeah.
That's why we made the tensor product. That's what I understood from last time. Now here today we have H and I sequentially.
No. This is also.
Okay, look at that. We have in the Q.
No. Oh, sorry. I realized I was confused. No, we didn't do that sequentially. We still apply this parallelly.
Okay.
Sorry. I didn't make that clear.
Yeah, that makes sense for me now.
Yeah, it's yeah. A good question. Yeah, I didn't realize what compute. Sorry, I didn't make that clear. We actually apply that.
Yeah, that makes sense now. Thank you.
Yeah. Okay, actually, let me highlight that. That's yeah. So that's this one is green. Yeah. Oops, that's
yeah, that makes sense now.
Yeah. So we didn't do the sequential. It's actually still parallel. Yeah. So,
yeah.
Good question. Thanks. That actually really clarified.
Thank you for clarification.
Oh, sure. Yeah. So it's consistent. Yeah. So if we don't do this, we can do a tensor product 2H. That's a very complicated. Gee, that become a 4x4 matrix. It should give exactly the same result, but it's
it's a long one, yeah.
Yeah, it's quite a lot to write out. Yeah, so yeah. So good question though. So
thanks.
Yeah. So I guess we still have about half an hour. We can do another example, just help you prepare the homework, I guess. Yeah. So which one? Which example should I do? I'm going to do the CNOT with the Hadamard gate, and that one should also lead to a not entangled state. So let's do this example. So we first apply